In the last lecture, I showed you the shortcomings of the labeling algorithm, the Ford and Fulkerson's labeling algorithm. So, I thought that I will at least give you some idea about one of the improvements on that algorithm, because at this point of time Ford and Fulkerson's algorithm is not really used, because as I told you of its shortcomings. So, because the scope of the course does not really permit a very detailed discussion of max flow algorithms, I thought I will at least introduce you to one of the improvements that were made some time ago. So, here the paper, actually this was by Edmund and Karp, who have done a lot of work in optimization, combinatorial optimization, and their paper appeared in 1972 in the Journal of Association of Computing Machines, and the title was Theoretical Improvements in the Algorithmic Efficiency for Network Flow Problems. So, this would be a very generic, the kind of thing I am going to describe to you is a generic algorithm, but when you apply it to max flow, you see the advantage. And again, as I said, this is again only the first step of improvement. Then later on there were many more improvements, and it will be evident to you why this is not the last word on max flow algorithm. So, I will come back to the same problem that I discussed with you last time. And so, idea here is, you see, we were the Ford and Fulkerson's algorithm does not say anything about how you operate that list of nodes that you scan. So, here the idea given by Edmund and Karp is that you operate the list as a, so the idea here is operate the list as a queue, and you mean you know you understand what it means. That means first in and first out. Okay. So, when you operate a list as a queue, that means whatever came into the list the beginning, so according to in that order only it will go out of the list. That means you will pick up the, so here let me show you what I mean by that, and this is also known as a breadth first search, and then because of breadth first search we will see what the result is. So, here let us see, you start with list as including node S, then when you scan S, your list will contain nodes 1 and 2, right, because you can from S you can go to 1, you can go to 2, since there is no flow in the network right now. So, now when you say first in first out, I will now take out node 1 for scanning. Okay. So, then in that case, so here okay, I do not have to label, you understand what I am doing. So, this is labeling 1 and 2. So, then when you operate when you scan node 1, from here you will be able to label 3 and 4, right. So, your this will become, see, this is what we mean by operating the list as a queue, right. So, it will be 2, 3, 4, right. Then you will now take out node 2 for scanning, and from node 2 you can, you see 4 is already labeled, 3 is already labeled. So, you cannot do anything from here. So, you will go to the next one, right. From 2 you cannot label either 3 or 4. So, I will go to 3, and from 3 you can label. So, then when you scan 3 you label T. Okay. And so, node T gets labeled, and therefore, your augmenting path is this, right. And so, you have see that the capacity, of course, when you do the actual labeling, you will also record the label from which the node from which this you reach T. So, therefore, you when you trace back the path, you also check the capacity, and it comes out to be 10,000. So, you will say that you have flown along the augmenting path S13T, 10,000 units of flow. So, therefore, this will become my flow along this path. Okay. And now, I start scanning again. So, you see here also, as soon as one augmenting path is found, they are going back to a fresh labeling. So, that defect still stays, that you are not finding more than one algorithm augmenting path in one iteration. So, therefore, the later algorithms make an improvement on it. So, here you see we will again start from here, then you can label. So, here list will be this, and then from here you cannot label 1, you can only label 2. So, the second iteration, this will be simply 2, right, and then from 2. So, when you want to scan node 2, let us see, from 2 I can go to 3 and 4, right. From 2 I can only label 3 and 4, right, and then when you scan 3, from 3 you cannot label anything, right, because 2 is already labeled. So, from 3 I cannot and I cannot label T because this is already saturated. Yes, right. I could label from 3, I could label 1, right, because I can reduce the flow. So, when you scan 3, so you have 4 and then you have 1, because 4 is already labeled. So, from no, sorry, I'm not talking of 4. All I'm doing is from 3 I can when I scan 3 I can label 1. So, that's it. So, it comes into the queue at the end of after 4, right. And now, when you scan 4, then your list will be T, sorry, this will be T and 1. I should not forget 1 because 1 is already present. So, T, or you can say, okay, again I should not spoil the order because then the whole idea is lost. Yeah. So, the proper would be, proper thing, the list would appear as 1 and T. Yes. And now, from 1 you cannot label anything because all these nodes are labeled. So, then I will go to T, and so, and in fact, since T is there already in the list, that means I have found an augmenting path, and in this time your augmenting path is this, and this also has capacity 10,000, right, because from T you came by 4, and to 4 you came by 2, and then 2 you came by S. So, 10,000 capacity, and therefore, you have found the max flow in 2 augmentations, just 2 augmentations, and the total flow of 20,000 units. So, this is the idea. So, therefore, now I can spell it out, that if you operate the list as a queue, that means you use first in first out search for your for scanning the nodes, then you also look, you end up getting. So, this obtains shortest augmenting paths. Okay, and shortest means, of course, number of arcs, because we are not concerned about the distances of the arcs here, it is only the number of arcs. So, you see this one, both these paths had 3 arcs in the shortest path, and in the earlier thing when I had shown you, see, for example, what were we doing when the labeling algorithm, see, I had found for you, say for example, I found the path S14T, right. This was an S1, this was S14T. So, S14T, and this had capacity of only 1 unit, right. Then in the next iteration, we said we can look at the path S2, because there is no hard and fast rule about how you find in the Forden-Fulkerson labeling algorithm. S2, then I can go to 4, 1 and T, right. This was your second augmenting path if you choose, again with capacity 1, right. And so, the flow at the end of these 2 would be 2, and now if you alternatively you alternate with these 2 augmenting paths, you will have 20,000 iterations, sorry, 10,000. If you do take this as a pair, then you are having 2 units of flow in the network. So, then you will have 20,000 iterations to get the flow that you got by using the list as a queue in only 2 iterations. So, the advantage is definitely there, and now I want to formalize this algorithm, that is, if you use breadth first search for looking for augmenting paths, then you can do a faster work, and this can be proved theoretically. And as I said again, the scope of the course does not really require that we talk about the actual complexity of this algorithm, but it will certainly be, you can prove that it is faster than say for example, the values of the arc capacities, the uij's, don't matter here at all, whether they are real numbers, integers or fractions. Whereas, in the Ford and Fulkerson algorithm, we could show finiteness of the algorithm only when the capacities were either integers or rational numbers. Okay. So, that is the point. So, here later on, when you are more interested, you can go to further to read more detailed courses about these problems, and then you can understand the complexity part and so on. Okay. So, let me now come to this breadth first search algorithm. Okay. So, idea here is, of course, S is your source node, T is the sink node. Then we will define D nu as the set of nodes that can be reached from S in exactly nu arcs. So, we are now going to define a set D nu, and we will say that the path from S to the node in D nu has exactly nu arcs in it. Okay. And it is very easy to construct such a set. So, let us start with D 0 as the node S. Then when if you are working with nu, then you go to nu plus 1, the next set. And how do you construct it? If there exists a directed arc I j for which x I j is less than u I j, or if there exists a directed arc j I for which x j I is greater than 0, and such that I is in d nu minus 1. So, that means what we are saying is that suppose this is your set d nu minus 1. So, node I is here, and I am looking for arcs which are either like this j, and node j should not be, see, I am iteratively constructing the sets d nu, right. So, then if I is in d nu minus 1, then j should not be in any of the d h where h varies from 0, 1 to nu minus 1. That means, it should not be in the set which have already been marked. Okay. So, so that means here, if here j is such, and if you have your x I j less than u I j, that means I can augment the flow on arc I j, then j does not belong to d h where h varies from 0, 1 to nu minus 1. This is the idea, right. And if the arc is, see, I is here, but the arc is this way, right, from j to I, then I can only again the whole idea is I can label j if provided x j I is greater than 0. If this flow is positive, then from going from I to j, I can reduce the flow on arc I j, and here again j should not be in the one of these sets d h, which is h varying from 0 to nu minus 1. This is the whole idea, right. So, then I will put all such nodes j due to the set of all such j, and mark each node j belonging to d nu. So, I had constructed up to d nu minus 1. Now, I am showing you how to construct the set d nu, okay, and by recording its predecessor node. So, for example, for node j, I could label it from node I. So, we note down the predecessor node, right, and if no such arc I j or j I exists, then you set d nu to be empty. Okay. If I can't find any arc I j like this for which x I j is less than u I j, or for which, or an arc j I for which x j I is greater than 0, then my d nu would be empty, and I will stop. I will say that I have no augmenting path. So, if d nu is empty, terminate, no augmenting path exists, right. And in this case, we will show that the current flow in the network is actually the max flow. If t belongs to d nu, then stop. An augmenting path has been found. Use the predecessor node to trace back the path from t to s and find its capacity. Go back to step 1. So, then we will start all over again to find C. So, here now, yes, a breadth first search, again I am giving this to you as a new algorithm, just to because the labeling algorithm is not considered to be efficient. But here, if you want to know why this will give us shortest paths, then of course the you have to have a little idea of the graph theory and the search techniques, which again we are not talking about. But anyway, it does not matter. You can, if when you work it out on a network, you will see, and when I show you the examples, one of the examples I will consider here, then you can see that yes, this kind of search helps you to find the shortest augmenting paths, and then in one iteration, suppose you find shortest the augmenting paths of length, let us say 4, then in the next iteration you will find augmenting paths of 4 or 5, or what the length will go on increasing, and that is how it shows that the algorithm, these are finite. In fact, this algorithm will be efficient, and more efficient algorithms can have also been constructed, as I told you, because then in the newer algorithms you are searching for augmenting paths, more than one augmenting path in the same iteration. Okay. So, now let me work out an example for you to show you the steps. So, I hope this is okay. So, essentially we are saying that we will always, whatever admissible arc, essentially in other words you can say that from node I, all admissible arcs, then the corresponding nodes will be set in the next set, and then you will once you have constructed the set d new, then we will go to the new set, and because you will come back here, you will increase the index here, and then we will again find all admissible arcs from the nodes incident on the nodes in d new, and finally if either we find we are able to label T, or we say that we cannot, one of the sets comes out to be empty, and then we stop, right. So, let me work out an example here. So, let me show you the method that I had outlined, breadth first search algorithm through this example, and you see the flow is given to you. So, the first number is the capacity uij, and this is xij, the flow. Currently flow in the network is this. Let us start labeling using the breadth first search algorithm. So, d naught, this will be 0, the label for this one for starting node. Then you see from here, this is saturated, this is saturated, this is the only one. So, I will label this as 1. So, node 2 gets labeled, right, and so my list is being prepared like this, and we are saying that first come first out. So, this will be now from 2 I try to now label. So, you see here there is a leftover capacity, here there is a leftover capacity, here also, and here. So, that means you can label all the nodes, and let me write it as 1, 3, 4, 5. Okay. And then we will now pick up the node 1 from here. So, d 2 is this. So, let me write the labels for all these as 2. So, 2, 2, 2 and 2, these are the labels, right. Now, you try to you pick up the node 1 from here, first in first out. So, 1 can you label anything from here? Yes, you can label 6 from here. So, I will write 6 here, right, because 3, 4, 5 are already in the list. I will put 6 at the back, fine, that is all. Then you start from 3. You pick up 3, you can label 4 is already labeled, 6 is already labeled. So, that is it, 2 has already been labeled. So, you cannot do it. So, 6 I will put the label as 1. Oh, okay. We were also doing this, that you put this and then you also put the level at which the the label has been put. So, this was 1 1. Actually, that is what we were doing, right. This will be 2 2, and this is also 2 2, because all are being labeled at level 2, they are in d 2. So, I should put this as 2, and this will also be 2 2. Okay. Then when you label, now the third level labeling, you start with 1. So, this will be 1 6 1 3. Okay. And you are not done with level 3 labeling yet, because from 3 now you cannot label anything more, 4 also you cannot label anything more, from 5 you can label T. You see, from 5 you can, because 4 and 6 are already labeled. So, 5 you can label T, and therefore, the label for 5 would be T would be 5 and 3. So, third order label, and the moment you label T, you have T has been labeled. So, an augmenting path has been found, right, and the augmenting path is S to 2, 2 to 5 to T, and of course, we trace back, because from T you will go to 5, right, from 5 you will go to 2, and from 2 you will go to I should have put here S. S. From 2 you came to you came to 2 from S, and the capacity then you will have to find out, because you start going about see here for example, the capacity leftover capacity is 1, then you will see if you can flow that much unit back up to S. So, therefore, this is the augmenting path with capacity 1. So, we will now need to augment the flow. So, let us quickly do it. The flow becomes here 4, okay. Then this you have 1 unit of flow here, and this becomes 4, right. So, then it says you erase the labels. This is again, as I will show you, the better algorithms exist, which also do not say that you erase the labels the moment you have found one augmenting path, because that again is lot of duplication of work. So, we will not be able to talk about that algorithm, but such algorithms exist. Okay, fine. So, now we start labeling the nodes again, and you start with this as 0, then here again you can only label this. So, this will be S and 1, level 1, right. Then from 2 you can again label 1, 3, 4 and 5, because here again you have leftover capacity here, here and here. Okay. So, I label these, and of course, the labels would be here 2, 2, you see. So, therefore, you are repeating so much work. So, this would be because you have flow from 3 to 2, therefore, you can label 3, because you can reduce the flow here. So, this will be 2, 2, level 2 labeling, right, and then 4 also gets labeled 2, 2, and this also gets labeled. So, the same thing, you need not have reduced erased all these labels here, fine. Now, we will this is saturated. From 5 I can label 6, and that is what we did here. So, 6 came here from 5, 6 came to the list D 3. Actually, I could have removed 3, 4, 5, there was no need, because D 3 is 6, right. And then from 6, when you, because here 6 again you can label T now, because there is some leftover capacity. So, D 4 is T, and therefore, augmenting path of length 4 now. Here the augmenting path was of length 3, it used 3 arcs. Now, it is augmenting path of length 4. So, when you label again, the path length will go up, and the augmenting path is now S 2, 5, 6 and T, because here you came from this was 5 and 3, right, and the label for this became 6 and 4. So, 4 length, so the path length keeps increasing every time you label. So, here then the cut, corresponding cut is S, because so now when you want to label again after you have okay, what was the capacity? Capacity of the flow is 1. So, this will become 9, this becomes 2, and this becomes 2, and this is 5. So, please make sure that you have, so that means 11, 7, 18, 18 is the flow, and you can see here also 9 plus 9, 18 is the flow. And now, when you want to label again, D 1 is not empty, because D 1 is not empty, because I will be able to label 2, that will still be there, fine. So, I should not say this, D naught is this, D 1 is 2 again. If its numbers are I do not know, maybe the initial flow 18, and so then can you again find so now you will not be able to find, yes, now you try to label, we will stop here, but D 1 is certainly not empty. Now, from D 1 can you label anything? From 2 can you label? Yes, you can label 1, you can label 1, and then you can label 4, again you can label 3 and 5. So, how did I write? So, therefore, this is not correct. That means, your D 3 D 2 is again 1, 3, 4 and 5. because all these numbers there are from 2 you are able to label 1, you are able to label 4, 5 and 3, because here again this is it, right. Fine. So, then fine. So, now we want to label from 1, I cannot do, I can label 6. So, here again D 3 will be, so I will write 6 at the end, 3, 4 and 5. Yeah, I should keep removing the nodes which I am not using, right. And then again you want to label and something, can you label something from 3? Can you label something from 3? 4 is already labeled, 6 cannot be labeled, everything is done. So, 3 is gone. Then from 4, can you label anything? You can label, 5 is already labeled, 4 you cannot label anything. Then 5 you cannot label this, you can, 6 is already labeled, and that is it. So, this is it. So, now this, therefore, your D 4 is empty. D 4 is empty. And so, the cut, remember we would say that the cut is all union of D 0, D 1, D 2, D 3, because the list you keep dropping the nodes from which you have already scanned. So, D 4 is empty, right, and therefore, your cut is actually 6. So, it will be S 1, 2, 3, 4, 5, 6. So, this is the cut, this is the cut. Okay, because your cut, right, remember we said that you add up all these these sets, and then so this will give you, and because now you do not have anything, any valid arc from 3 to 4, because they are all saturated, and this is what we will just write down and show you the validity of this. But this is a verification, and so therefore, the current flow in the network is 18, the max flow in the network is 18. So, just want to give the last comments on this, and I have already shown you through this example. What we are saying is that the moment, see, we said that here that when you hit the set to be empty, the D nu set is empty, then you stop and see what is happening. Why is D nu empty? You can just see that from node I in D nu minus 1, whatever arc is there, I j is a forward arc, then you see it is already saturated. So, therefore, you are not able to label node j, right, and so you cannot find any node in D nu this way, that means which is connected to node I through a forward arc. Similarly, there is no j which is connected to node I in D nu minus 1 via backward arc, because the flow x j I is 0, and therefore, I cannot label j from I. This is what is happening, and so my D nu is empty. Right, I am not able to label any more nodes from nodes in D nu minus 1, and so D nu is empty, right. And you can see that the cut would be, you add up all the D naught to D nu minus 1, add union of all these sets, then this and V minus this set, this will give you the cut. And see, the thing is that D 1 is only connected to arcs in D 2 and so on. So, essentially no problem, because you do not have any arcs from here to nodes here, right. You only have arcs from D nu minus 2 to D nu minus 1 and so on. So, this is a cut, and the cut set will of course will be the edges like this, which are either forward arcs from nu minus 1, nodes in nu minus 1, or arcs coming into to nodes in nu minus 1, but the arcs coming into have flow 0, and the arcs going out of nu minus 1 are saturated, and therefore, this satisfies the conditions for the max flow min cut theorem, and so this must be the minimum cut, right. And now, you see that as I showed you through the example, of course, these two things we will not, this is not part of the course to be able to show you that, but you can see through this example that because of the labeling, when you exhausted the possibilities of labeling finding augmenting paths of a certain length, then next time when you started labeling, the length went up, right, from 3 to 4 in this case. So, here also therefore, you see the number, and since the path length cannot be more than n minus 1, Therefore, the number of iterations will be bounded above by the number of nodes in the network, right. And then you can also show, it is possible to show that the amount of work that you do at each iteration, because you are after all just trying to scan all the edges which are either coming in here or going out, either going out or coming into this. So, then the amount of work that you would do will not exceed order v square, the number of nodes square. And so, the total complexity or the time required to work out, that means the number of basic steps that you would need to work out this algorithm would be into order v cube. I am just giving you an idea, of course, we are not going into all those things. So, this is the whole concept behind trying to improve on the Ford and Fulkerson labeling algorithm. And then, as I said, there are bit more refinements on this, which make the algorithm more simpler to implement. So, let me now talk to you about topic PERT and CPM. This is called critical path method and program evaluation review technique. These are used, this is these problems arise in project managements. You have huge projects, say for example, at some point it was sending a man to the moon. It was a huge project, and you can imagine that such a project would entail 1,000 different jobs, which could be done in small teams independently, and then but whole thing had to, the whole effort had to be coordinated. And you can imagine a project manager or who has to oversee the whole project, anything of that magnitude, a project would cannot just work without having some support in the form of. So, therefore, in the form of the techniques that we are going to talk about today. And my reason for including this in this course is that you can see that some of the network techniques that we have learned and the linear programming formulations, we can help you to formulate these problems in a way, so that you can try to find solutions, and you can provide some sort of guidance to a project manager who would otherwise be simply helpless, because he will not be able to, he or she will not be able to otherwise take care of how something, if something is going wrong, something is getting delayed, or something can be done in a faster way, then the whole idea, the project should not get delayed unnecessarily. And if you have a schedule, somehow if you can manage to keep up to the schedule, and all these aspects are there. So, I will try to just give you a few examples, so that you understand where these situations can occur. So, here the first I will talk about the critical path method. Okay. So, this is the critical path method. So, a large project gets divided into activities which we think are sort of in a way independent. That means, different sets of people or different resources can be given to these small tasks or jobs, which can be done simultaneously. But obviously, you need, so what are the things that you define? You have to define your activities or jobs or tasks, whatever name you want to give to them, right. So, you have to first define these, and then you have to have some sort of precedence relations among the jobs. Okay, not a very good precedence relations among the jobs. Say for example, if you are building up a, or okay, let us say a tire has punctured on the way, you are going somewhere and a tire gets punctured. So, you cannot, for example, replace the tire, or the, unless you take out the stepney from the dicky of the car, right. And you cannot put the stepney unless you remove the punctured tire, the wheel from the, first you have to remove the wheel from the car, and then you have to remove the that and replace the stepney, fix the stepney to the car, and so on. So, the sequence of jobs is also fixed in a way, and here I am talking of a situation where sort of the jobs are definitive. We know exactly what resources, how much time and so on the jobs will require. And so, here critical path method is mostly used for situations where situations the things are very deterministic. Okay. So, precedence relations among the jobs are required, and I would like to use the presentation for these critical path method problems by saying that, for example, a job or an activity will get denoted by a pair of nodes, right. So, for example, so here first of all, when you define I represent the job ij. So, this is ij represents a job. Okay. Node I is the start of the job, right, and node j represents, well, okay, maybe it's enough to say that node j represents the finish. Okay, it represents the finish. Say, for example, yes, suppose I have an arc like this also here. So, let us look at this network here representing a project. I have not shown the finish here. The finish may be somewhere, and then you may have something like this. This may be the finish. So, here you start, and what it is saying is that activities S1 and S2 can begin at the same time, because the resources and the kind of team that you require for starting these two jobs, they are different, they are independent, and so you can begin the project from this at point of time, and both these activities can start at the same time, right. Then TS1 gives you the time to complete this job. TS2 denotes the time to complete the job S2, right. And then now I am trying to show you the precedence relationship. So, what it is saying is that job 1-3 cannot begin till job S1 is complete. Okay. So, this is kind of precedence relationship, and here for example, in this case we are saying that node 3 is the beginning of job T34, of job 3-4 and of 3-5. So, when I say that for node ij, if you have this arc ij, then node I is the start of the job, then it can be the start of more than one job, right. So, normally nodes are treated as events. That means, at node 3, this is the beginning of both the jobs 3-4 and 3-5. And when I do this broken arrow here, that means this is a dummy job. Okay. This is a dummy job, because in this network I want to depict the precedence relationship that jobs 3-4 and 3-5 both require that job S2 and 1-3 should get completed. Both the jobs have to be completed before jobs 3-4 and 3-5 can begin. Okay. So, therefore, by doing this and saying that it requires no effort, no resources, so I am putting a 0 here, that means the duration of this activity is also 0. So, therefore, this now shows that the jobs, the event 3 can take place only once the jobs 1-3 and S2 are completed. Okay. And then this 2, and so what I was saying is that here, for example, at this point I can say that this is also the finishing point of time of job 3-5 and 6-5, but actually node 5 denotes the finishing of both the jobs 3-5 and 6-5. So, this clarity has to be there, right. And then of course, you have activity 3-4, and then this you can call it say this will be 6, this will be 7, node 7. So, then all these activities, when they get completed, then you have the project gets completed, right. So, here this is the representation, and the precedence relationships will be depicted by this kind of node arrow arc, node and arrow arc, and then precedence relationships among the jobs are specified. Then here sometimes dummy jobs with which with 0 duration may be used for depicting precedence relationships. Precedence relations. Okay. See, while discussing PERT CPM, I did give you an idea how we would go about drawing the network, but here let me give you formalize the whole thing. So, we are using the representation where the nodes represent events, and so we will have a node. First we will have one single node to depict the or represent the start of the project, and then of course, the arcs connecting nodes are activities. For example, here I j will represent activity I j, which begins at node I and ends at node j. Similarly, activity L j will also will begin at L and end at node j, right. So, arcs connecting nodes are activities, and then precedence relations are indicated by activities acting at the node which represents start of the activity that follows immediately. So, for example, if you have the activity some j k, then j k activity cannot begin unless both activities I j and L j end at node j. So, therefore, when two arcs or more than whatever the number of arcs which end at a particular node, they all represent the activities which are immediate predecessors for the activity which begins at node j. So, this is the kind of precedence relationships we depict in the network, and then we often use dummy activities to show precedence relation. Now, for example, for activity j m, activity I j and I k both are predecessors, but then since activity I k is also a predecessor for activity k n. So, therefore, in the network I have joined k and j by a broken arc which denotes a dummy activity. So, now the network shows that for activity j m, activity I j and I k both are predecessors, immediate predecessors. So, this is how, and of course, in the beginning when you are drawing the network, you can use the dummy activities freely, and then again you can revise the whole thing and see if you can omit some of the dummy activities, right. Then numbering of the nodes is done from top to bottom. So, essentially what you do is you first draw the whole network showing the precedence relationships and so on, and then you start numbering the nodes from top to bottom, and then there should be a node indicating the end of the project, fine. And then of course, as we discuss the problem later on, I also show you some of the ways how we manage the network. Okay. So, this is so therefore, we can have this node arc representation, and this sort of gives you a feeling of the flow, that how the work is progressing, and then you can chart it out and you can see it from day to day, how the or from month to month, whatever your time unit, how the project is progressing. So, this gives an idea to the project manager. Okay. Now, the finish time you can see here. Yes. So, this will tell you the when you reach t, that means the time time to complete the project will be the length of the longest path from start to finish. And so, remember I told you that we would need to compute longest paths in a network. Yeah. So, now let me make two comments here. So, first of all, a project will be completed only when all the jobs have been completed. So, which makes so therefore, it you immediately realize that the longest path from S to T will give you the duration of the project, right. And secondly, this network is acyclic. the the project network, maybe I can, the project network is acyclic. Why? Why is it acyclic? See, if it had cycles, that means what? That means your precedence relationships are faulty. No, if you had a cycle like this in your project network, then that means what will it say? It will say that this job must be completed before this job can be completed. But then this is the immediate predecessor of this, which means that this job can only be that this job can start only when this job has been completed, right? But this job could not start before this got completed. Now here, if you have this kind of cycle, obviously the precedence relationships that you have defined are not valid. So the presence of, when you start drawing the project network, the moment you encounter a cycle, you'll realize that your precedence relationships are wrong. There's something, and so you should go back and revise them and then draw the network again. So these are, so therefore, and once you know that the project network is acyclic, there is no question of a positive cycle present in the network, and therefore longest paths can be found. And you know that you can just do the minus of theCijs, or here the Tijs, and you will be able to apply the shortest path techniques and find them, right? Okay. So now just to show you a few computations, how to we find out the longest path. So here, because the project is acyclic, the finding the longest path becomes very straightforward, and so I'll show you that just by simple labeling. We don't really have to go back and change the Tijs to minus Tijs and apply the Dijkstra's algorithm, any one of them, because we can do a faster job here. So, and so I would like to remark here that, see, all along this course you have seen that we have the theory developed for solving a certain class of problems, but when you have special features present in the problem, it helps to exploit those special features and come up with faster or better algorithms. And so that's what is happening here. To find the longest path, we will show you the quick way of doing it. So here, let me start defining Ej is the early start of node j. So now I will not refer to the job here right now, because as I told you, for example, node 4, here it is the start of job 4.6, jobs 4.6, 4.7 and 4.5. So I'll just simply say early start of node j, right? Let me define Ej. So which means that here we will always say that Es is 0. Let me start, the clock begins from 0 time, right? And then we will use this definition that for any node j, you want to find out the early start. And obviously, for example, here this node cannot begin, the start for this node cannot begin unless jobs 2.4 and 1.4 have completed, right? So therefore, the definition would be max of Ei plus Tij, where I is, so yeah, I should have maybe defined the word immediate predecessor. So this is immediate predecessor, means that here, for example, for 3, the immediate predecessor is 1, right? Or you can say that for job 1.3, the immediate predecessor is S1 in terms of jobs. So you can have both concept of immediate predecessor node or predecessor job, right? So here, and so for example, for 5, both this and this, 3 and 6 both are immediate predecessors for node 5, right? So when you want to find the early start for node j, then what you are saying is here, so you have a node j here, okay, and you will look at all the immediate predecessors here, I1, I2, say for example, and then early start of this plus, so this will be Ei1 plus Ti1j. Similarly, this will be Ei2 plus Ti2j. So this will be Ti2j. Okay. So you will take the max of the two, because remember, this node cannot begin unless both the activities which are coming into the node are completed. Okay. So, therefore, this will be max of E I plus T I j, and I is an immediate predecessor of j. So, let us quickly write down, say for example, here there is no problem because this is 0. So, start is 0. So, I will write the numbers as this and then I will complete. So, here this will be 2. Yes, because this is 0. So, this is 0 here and then this is. So, similarly here it will be 4. Yes, right. And now let us come to node 3. So, node 3 here again there is only this predecessor. So, there is no question of max. So, this will be simply 6. Yes, and I am not completing the other part, which we will do after I define the fine. So, now for node 4 for example, this way it is 5, right, this one, and here it is 7. So, I have to take the max. So, this will be 7. Okay. And then for this one for example, this is 4 plus 4 8, and here this is 7 plus 7 14. So, again I take the max. So, this node cannot begin before, if you are talking in terms of days, let us say for example on the 14th day only, because after 14 this early start is this, right. Then if you now come to node 6, then here this is 7 plus 6 is 13 and 7 plus 5 is 12. So, 13 is the larger number, therefore, this is this, and finally, you come to the finish. So, the finish part here will be, we have to add 10 plus 14 24, then here this is 15, and oh, I did not write down the number for 6 7. What is the number for 6 7? Does not matter, maybe we can write something here and then we can correct it. Yeah, okay, maybe it is 7, right. So, then this will be 20 and this is 15 and this is 24. So, this is 24. Okay. So, this gives you the early start of all these nodes, and so the earliest your project can finish is on the 24th day. Okay. And similarly, now thing is that I can also now talk of the late finish and then the late start for each node. So, then the calculation would be backward, and I will say that, let us say that this is equal to early start. Okay, I am using the node T, usually again the same concept, sink and source, so source and sink is used. I have written 7 here, but so if you take this the fact that a late finish is also the same as early finish, given that, or sometimes what happens is there is a due date for the project. So, then the late finish can be taken as the due date of the project, and then you compute backwards, and the computation is again straightforward here. Now, you will be taking the minimum, but then it will be immediate successors. See, what we are saying is that if you have a node I here and you want to compute its late finish, then you have jobs like this, right. And so, you, because all these jobs have their late finish, this nodes, and then you will subtract the completion time of the each of these jobs and take the minimum, because again you see this node, the latest finish can be only when all these jobs have completed. So, the completion times of this and the late finish of these nodes, and then minus the processing times of these jobs, and then you take the minimum, right. So, for example, here I will just quickly do computation for one node, see 24, and if this is 7. So, here you see this is 24 minus 7. So, this will be 14. You get my point, because here this node is only one successor and this is 24 is the late finish. So, minus the completion time of this job. So, that is 14. But for example, for this one, when you do it, so here or come to this point. So, this is again 24 minus 10, which is 14. Okay. And for this one it will be, yes. So, here now you have to do it this way. At this point it is 14 minus 5, which is 9. So, one number is 9. Then this is 24 minus 8, this is 16. Can you see it? 24 minus 8 is 16, and then so that is it. So, these are the two immediate successors of job 4, and so you have to take the minimum, which will be 9 here. Sorry, and then sorry, for 4 there are 3 immediate successors, 6, 7 and 5. So, 5 it is 7 minus 14 minus 7, which is 7. So, actually the minimum of the, So, therefore, this will be 7. Okay. And similarly, when you go back here, you will see that this will come out to be 0. So, here this is 7 minus 3, which is 4, and here because only one immediate, 2 immediate successors here, yeah, here you should have computed this. 14 minus 7 is 7, right, and then here this is only 2 immediate successors. So, this is 7 minus 4 is 3, and 7 minus 3 is 4. So, the minimum is 3, right, and then this is 4 minus 4 is 0. So, therefore, because here this was 1, so minimum again is 0. So, this is your computation for the late finish and early finish, and but at least you see the what was your path that you found out. I will quickly just see 24. So, this was this, then you had this, and we had this one and this. This was the longest path. Quickly, 7, 7, 14 plus 10, 24. This was your longest path, and so we call this the critical path, because if any activity on this path gets delayed, then your project gets delayed. All others, you see there is some sort of slack, which I will define in the next lecture, but this is the concept. So, the longest path could be found by simple labeling algorithm, which did not take long time, and then because the network is acyclic, and so now we will show you how to do some more analysis for this problem.